What's going on, everybody? High Peak Education coming at you again, this time with a intensity of radiation question calculation. The sun delivers 1,000 watts per meter squared of energy to Earth's surface. A. Calculate the total power incident on a roof of dimensions 8.00 meters by 20.0 meters. B. Determine the radiation pressure on the roof, assuming the roof is a perfect absorber. C. What is the force on the roof? Okay, well, first of all, this 1,000 watts per meter squared energy incident to the Earth's surface, that's going to be a power per area, and that's going to be an intensity. So this is an intensity. And remember, this is meant to be an eye, but it's sort of a double-backed eye because it's not electric current. So this is 1,000 watts per meter squared. It's power per area. So notice that if we want power, which is what we want in part A, we want to take the power from taking the intensity multiplied by the area. And the area is going to be length times width. Okay. So I think we can put the numbers in directly. So the intensity is 1,000 watts per meter squared, which, by the way, at the top of Earth's atmosphere at the equator, the so-called solar constant is measured to be somewhere in the 1361 to 1365 range. So this is a pretty large value, but still a realistic value that could arrive at Earth's, say, equator. Let's say on the middle of a summer day. And then we need times length times width. So that's 8.00 meters times 20.0 meters. Okay, so that will give us the power. So let's get the power. So the calculator shows us 1,000 times 8 times 20 should be 160,000. So that's 1.60 times 10 to the 5th watts. That'd be 160 kilowatts, or it's 0.16 megawatts. It's quite a lot of power. Part B, determine the radiation pressure on the roof, assuming it's a perfect absorber. Well, if it's a perfect absorber, the pressure, notice this is not power, right, or momentum. The pressure on the roof should be the intensity divided by the speed of light. So watts per meter squared divided by meters per second should give newtons per meter squared, which is pascals, which is pressure. So that intensity was 1,000 watts per meter squared divided by 3.00 times 10 to the 8th meters per second. Okay, so let's get this number as well. So 1,000 divided by 3 times 10 to the 8th. Okay, so we'll write this down. It's approximately 3.33 times 10 to the minus 6th, and that's going to be, again, pascals. And remember, pascals are the same unit as newtons per meters squared. It's the units of pressure. Lastly, part C. What is the force on the roof? Well, force divided by area is pressure. So force is equal to pressure times area. So we can just take that area we did before, 8 times 20. So 8 times 2 is 16 with a 0 on the end. That should be 3.33 times 10 to the minus 6th pascals times the area of the roof, which we said was 160 meters squared, which again is just 8 times 20. All right, so let's multiply those. For our final calculation of this problem, 3.33 times 10 to the minus 6th times 160. Okay, so 5.33 times 10 to the minus 4. 5.33 times 10 to the minus 4, and that would be newtons. So that's like 0.533 millinewtons. That's a pretty small force. There is force on the solar collectors on a roof that's, let's say, got solar panels on it, but the force is very small and the pressure is very small, despite the power being delivered being quite large. Okay, so just kind of keep that in mind. All right, everyone, thank you very much for your attention. Please smash that like button if you enjoy this content. Please share this content amongst your social network. And please subscribe to grow the channel. I look forward to reading your comments, and I will see you in the next video.